Okay, so today's session is not about a specific topic, but like I've said before, there's so much material in IB chemistry to kind of learn and retain that anytime you can minimize what you have to memorize by understanding the concept and not having to memorize every single pathway to apply it, it's really useful to be more efficient in your studying and more efficient in kind of your memory because you've got a lot of stuff to memorize for 6 subjects or maybe 7 depending on how many you're taking. And so anything you can reduce in chemistry, the better for your chemistry and all your other classes as well. And so today's lesson is just kind of going through a bunch of these topics and going, okay, here are things that you can think about that will help you kind of reduce what you need to know. Okay. And so it may be a little bit all over the place, but I'm going to try to go in sequential order unless I think of something later on that I'll add in. But okay, topic 1. Okay, I think the biggest thing about topic 1 is stoichiometry. And no matter how you do stoichiometry, the fundamental aspect is it's all about conversions. Whether you do factor label or you call it railroad tracks or you do proportion method or even if you do rice charts and stuff like that, it's all about conversions. And the thing you really want to focus on here is there isn't an infinite number of conversions that you have to deal with in stoichiometry. There's a very limited number of conversions that you can use, and with stoichiometry, it's a very linear process once you practice it. And so instead of memorizing, okay, how do I get from grams to atoms? How do I get from grams to moles? How do I get from atoms to grams? How do I get from atoms to moles and stuff like that? It's all the same process with just different conversions. And so what you want to think about is the conversions that are always available, okay? So the conversions that are always available that you should think about that aren't explicitly stated in the problem are the following. 1 mole is 6.0223 times 10 to the 23 particles of that species. So if I say there's a mole of something, that means I have 6.02 times 10 to the 23 of that specifically. This is where units come into play a lot. Because if I say I have 1 mole of CO2, that means I have 6.02 times 10 to the 23rd molecules of CO2. But that also means I have 3 times as many atoms because every 1 molecule has 3 atoms. So really important to kind of maintain your units throughout because you can lose track of what species you're talking about and that causes mistakes in your calculations. Usually the first question on every multiple choice is kind of one of these conversions. And so you should expect it and you should be prepared for it. And they'll find ways to kind of make it more challenging for those that haven't memorized certain things. Another conversion, okay? At standard temperature and pressure, the molar volume of a gas, specifically a gas, is 22.7 decimeters cubed, per 1 mole, not per 1 decimeter cubed. Okay. So 1 mole of gas occupies 22.7 decimeters cubed of volume. But this is only for gases. Don't mix this up with solutions and things like that. So that is also always available to you. Also that's available to you is molar mass. Whatever the mass on the periodic table of that substance is the equivalent of 1 mole of that substance. Okay. I'm going to try to make a concerted effort to speak slower for those 2x YouTube watchers because apparently I talk too quickly to be sped up to 2 times. So I'm going to make a more concerted effort to enunciate and speak more slowly.
I tried it, Mr. Chong, and I can't understand you. It's like 1.5. That's your ideal.
That's what I've heard is the max, 1.5.
No, you can do 2 times, but you have to like build your way up to it. You do a couple of minutes at 1.25, and then you go up to 1.5,
Okay.
and then 0.75.
Yeah, so Perrin, you have to ramp it up.
Yeah.
So slowly work your way up. You can't just jump from 1 to 2. You have to go 1, 1.25, then 1.5, and then we keep accelerating.
I don't have the time for that.
Okay. So molar mass is also another conversion you want to think about. Mole to mole ratio. If you're given a balanced equation, you will always have the coefficients that allow you to convert from one substance to another substance. And this is the most vital one for that, okay? This is the only way to convert between substances. So if you're ever going from one substance to another, in somewhere in your calculation, you have to have a mole to mole ratio. That's kind of the focal point of your calculation. So whatever you start with, your goal should always be, I need to find a way to get to moles. Because once I get to moles, I can convert it to my other substance and then go from that. So that's really important if you're calculating the ratios of substances in your reaction. It should always be toward moles. Okay. The ones that are problem dependent, okay, depending on the problem that you're doing, you may be given certain units and things like that. You may be given molarity, which is moles per 1 decimeter cubed. So if I give you a molarity, that implies that that is the number of moles. So if I say X molarity, that's the number of moles over 1 decimeter cubed. So if I say 5 molarity, that means there's 5 moles of that substance per 1 decimeter cubed of solution. Okay. You may also want to know that 1 gram is equal to 1 centimeter cubed of water. So if you're given a volume of water, you can say, or usually of solution as well, usually they'll say assume the density of the solution is the same as water. And so water has a very special value where it's 1 to 1. Every 1 gram of water weighs 1 centimeter cubed. I mean, it has a volume of 1 centimeter cubed, excuse me. If you are doing a gas to gas conversion, you can actually do decimeters cubed of A to decimeters cubed of B. It's not a mandatory one, but the gas ratio is the same as mole to mole. Because every gas occupies the same volume, so therefore the mole to mole ratio is the same ratio as the volume to volume ratio. That one's kind of specialized. You don't need that one, but I'm just trying to think of the units that you might encounter for this. But yeah, so every problem kind of revolves around these specific like values. And so the always available ones I want you to kind of focus on. The problem dependent ones have to be given in the problem. So you can kind of write those down whenever you need them. But these always available ones, it's really only what, 4 values: the mole, definition of a mole, molar volume, molar mass, and the mole to mole ratio. Those should always be in your mind if you're doing stoichiometry. They're not always stated, but they're implied that they're available for you to use. So if you ever get stuck on a problem, use one of these conversions based on what you're given and slowly work towards something that you can use. It's all very, very linear when you're doing that. I'm not going to do some problems right now, but I just kind of want to emphasize that concept. Okay. Questions so far on that? Okay. The second thing I would say is empirical formula. That's the second big thing: empirical formula, molecular formula calculations. And to really simplify this, all you want to say is you want to convert every element quantity into moles. So no matter what values they give you, your goal should be to convert everything to moles. Because once you get everything to moles, then you can find the ratio between those, which happens to be the subscript. Okay. So once you get to the moles of every substance, then you can assume that that's the case. Now, also, if you're given percentages, you can just make those grams. So if I give you 75% carbon and 25% hydrogen, that's the equivalent of saying 75 grams of carbon and 25 grams of hydrogen. And then you can proceed with that conversion. Because once you get to the moles, you can find the ratio between that. Because if you get to like 0.25 moles of carbon and 0.75 moles of hydrogen, then you just divide by the smallest number. And then that becomes your subscripts. Don't round too much. You may have to multiply them all to get a whole number ratio, but that's the idea. It's just convert everything to moles, find the mole to mole ratio, and if you need to multiply to convert to a whole number, then you do that. But usually it turns into whole numbers here. And you should always have one, by the way. That's kind of one of the things as well. If you don't have a one somewhere, then you didn't divide by the right number. Like it should always be the smallest one so that you always get a one. And this is moles of atoms, okay? Not diatomics, just literally one atom of each. So you're using the molar masses of individual atoms. Yes, Alexandra. Are you saying in the moles, or are you saying like in the end of the very end of the problem? I would say if you're within a tenth of a whole number, it's okay. Yeah, but if you end up with 0.33 or 0.66 or 0.5, then you need to be multiplying by a number. The numbers are very intentionally designed so that you get a very nice number. So like, yeah, if you get like 0.25 for something, you did something wrong. Maybe you rounded your numbers or moles too much. I would try not to round those numbers as much as I could when I'm doing those calculations, just so that you don't get off, because you'd be surprised how much truncating one significant figure can affect your values, right? So just keep that in mind. Questions on that? Okay. Okay. Atomic structure, topic 2. Okay. So topic 2 is particles in an atom and the hydrogen emission spectra and calculating the wavelength and frequency and photons of photons. Things I want you to think about, okay? 1, the chemical symbol. Okay. This symbol itself can tell you all the information you need to know about an atom. Okay. 1, your mass number. 2, your atomic number. And 3, your charge. These 3 values allow you to solve for the protons. Oops, let me kind of color code here. The protons, the electrons, and the neutrons. Because these values tell you something about the atom, because the atomic number is the protons, because the protons determine the identity of the element. So that always stays the same. So your protons are always based on your atomic number. Your mass number is the mass number of all the particles that have significant weight, which is your protons and your neutrons. So if your atomic number is 9 and your mass number is 19, then your neutrons will be 19 minus 9, your mass number minus your atomic number. So you have 10 neutrons here. Now your electrons are related to your atomic number, okay? And I guess the way I would say it is protons minus electrons is equal to charge, because electrons are negatively charged and protons are positively charged. So if you subtract the number of electrons you have, that's the same as making them negative. So in this case, you would have 10 electrons as well. So this isn't so much as minimizing, but really kind of understanding these kind of concepts in this idea, because I think this is something that does show up a lot of the times as part of atomic structure on the IB exam. They'll literally just give you like 2 marks and say, identify the number of protons, neutrons, and electrons in the element or the atom. That is a typical question that they can have on the short answer, or even multiple choice, to be honest with you. So this symbol is super important for that. Questions? The second thing I want you to think about, and this is kind of minimize what you have to memorize, which is the hydrogen emission spectrum, okay? And the way I think about it is I just draw this out, okay? So the way I think of it is this. Oops. We'll do, sorry, my lines aren't super straight. Where n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, then n equals infinity. Okay. This diagram tells you a lot of what you need to know about Bohr's theory on the atom. Okay. Okay. So what does this tell you? One, it tells you energy levels are fixed. They are not variable. They are a fixed amount of energy. So there are fixed energy levels where electrons can reside. Okay. What else does this diagram tell you? Just by looking at this diagram, what can you tell about the energy levels and their values? As they increase, they converge, okay? Increasing means convergence. Okay. Is that what you're going to say, Daphne? Okay. So as you get further and further away from the nucleus, the energy levels converge closer and closer, which means the difference in energy gets smaller and smaller and smaller. What does an arrow look like to represent an electron on this diagram that emits light? Okay, downward, right. So going downward emits a photon, and that's what you see when you energize the electrons. You see when they come back down from their excited energy state, they emit a photon of excess energy. So electrons emit light when, I guess we'll say descending. Now, another thing, okay? Does anyone remember what type of light is emitted when you drop down to the first energy level? UV light, right? So there's UV light here that you emit when you jump down to level 1. And then what's the radiation that's slightly less energetic than UV? Visible. And then slightly less than visible? Infrared. So, wait, what'd you say? Okay. Did you say invisible? No. Oh, okay. Oh, man. Okay. So you want to think about that as well. When you jump down to certain levels, they emit certain light. So any jump down to 1 is UV, Any jump down to 2 is visible. Any jump down to 3 is IR. You don't need to know the names of those series like Pascan and Balmer and stuff like that. You don't need to know those names. You just need to know, okay, what energy level does it represent? Because they could literally ask you which of these arrows represents an emission of visible light. So you'd be looking from going higher down to 2. Okay. Now, how would you draw an arrow for ionization energy of an electron in the ground state hydrogen? How would you draw an arrow that shows the electron being ionized in there? So it's going to start here because ground state hydrogen. And where's it going to go? Up to where, Sammy? What is the definition of ionization energy, Sammy? Marissa? You have to remove the electron from the atom. Ionization energy is removing an electron from an atom. So yes, the symbolic nature here would be going to infinity. Don't draw the arrow past infinity. They're kind of sticklers about that. It goes to infinity because the infinity is the end of the atom, the edge of the atom. So ionization energy is the energy it takes to go from n equals 1 to n equals infinity. Yeah, because ionization energy defined as the energy required to remove an electron from an atom. And the edge of the atom is quote unquote infinity. Because once it reaches infinity, the atom has no more pull on it. So it's technically escaped the atom. Does that make sense, Alexandra? Okay. So really, all hydrogen emission spectrum is really based around this single diagram. And we get all these pieces of information from this single diagram of this, okay? So instead of kind of memorizing all these different words and bullet points, if you kind of imagine this picture here, you can kind of figure out a lot of information without having to memorize all these bullet points. Okay. Questions about that? Any clarifications? Okay. A little bit where it's appropriate. Yes, I'm going to weave some of that stuff in. Okay. Periodicity or periodic trends. Okay. The big thing here for SL and HL is understanding trends and explaining them, not just saying whether it increases or decreases, because you actually have that information available to you. So you don't actually have to know whether it increases or decreases. You have to explain why it increases or decreases. And so again, the emphasis is, and if you were here for topic 3, you know, you've seen this before, is when you go across a period, okay, the energy levels are the same because the period represents the energy level of the valence electrons. So energy levels are the same. What increases is nuclear charge, because you gain protons as you go across a period, which means more attraction for the valence electrons, which affects trends in whichever way that trend is talking about. If it's atomic radius and you're talking about the size of the atom, well, the more protons you have, the more tightly it pulls, therefore the radius gets smaller. If you're talking about ionization energy, well, the more pull on it, the more energy it takes for an electron to escape. Okay. Electronegativity. Electronegativity is the pull on shared electrons. Well, the smaller the atom is, the more nuclear charge you have, the more pull you can pull electrons away from other atoms. So all of this relates to that same concept. So again, instead of having to memorize 4 or 5 trends and then their results and explanations for each one, the explanation is the same every time. You just need to apply it to what you're talking about. As you go down a group, you increase energy levels, which increases shielding, and you have the same nuclear charge, because you have essentially the same ratio of protons to the outermost shell in all the elements in the same group. Okay. When you increase shielding and you're further away from the nucleus, you have weaker attraction. So that applies to whatever trend you're talking about now. Okay, atomic radius. Well, the size of the atom. Well, more energy levels by default makes the atom size larger. Ionization energy. Well, if we have weaker attraction for those valence electrons because they're further away, then it's going to take less energy to remove them, and that's why the ionization energy decreases as you go down a group. Okay. Electronegativity, the attraction for a shared pair of electrons. Well, the bigger the atom is, the further the shared pair of electrons are away from the nucleus. Therefore, you have a weaker attraction, so it's going to have a lower electronegativity. Those are the two ideas that you kind of really want to think about. And you can apply them to every single trend. Questions? There's not really a, oh, let's see. Okay. HL here. And I know we've only done this like in a Saturday session, but I'm going to jot it down here as well. If I were to kind of memorize this, I would think of something like, let's see, what would I do? Fe3 plus, okay, which is AR, oh, sorry, 3D6. And what I would think about is I would draw this out. Okay. So this is HL only, so SL kids don't worry about this, but I would draw this out because this is how I explain why why transition metals have colored compounds, because the D sublevel splits. And so these electrons will absorb light to jump up to the higher split D sublevel. And what you don't absorb, you see that color, okay? And this also helps because for this to happen, there has to be open spaces in the sublevel. So therefore you need partially filled D sublevel. So if I wanted to think about this, I would just kind of remember Fe3 plus and what its split D sublevel level looks like. Yes, Marissa. No, what I mean is that the D sublevels are no longer all the same energy. Some of them have a higher energy than others. So they split energy wise. So that difference in energy, electrons can absorb visible light to get up to that level. And then whatever light isn't absorbed, we see. Yes, for our purposes, yes. It can get more complex than that, but for the IB purposes, that's it. A split D sublevel. And that explains colored compounds. So this diagram kind of tells you everything. Partially filled D sublevel, split D sublevel, absorbs light to jump up, and then reflects light that you don't absorb. No emission of light. So there is no light emitted. This is not like the hydrogen emission spectrum. Questions on that? Okay. Topic 4, bonding. Okay, there's a couple of different things that I want you to really kind of focus on this. Okay, one is a super important thing: Lewis structures, because this is a vital part of understanding chemistry and being able to draw out Lewis structures with lone pairs and bonds correctly. Okay, and if you remember, from the topic 4 and 14 review, there is a specific method you can use to determine every single Lewis structure that you might ever have to deal with. Expanded octet or sub-octet as well. Okay, it's all about the budget of electrons, which is the number of electrons available. And then, how do I want to say this? The test structure, which is, let's see, how do I want to phrase this? The test structure, which is a trial and error version of the molecule. So it's the kind of most basic way the molecule could exist, and then you have to transform that to match your availability. Okay. So I will demonstrate this a little bit here. So you have to calculate how many electrons you have, draw a test structure that has certain characteristics, and then once you do that, you can manipulate it to match your actual allotment of electrons. So for example, I know CO2 is something that y'all all know already, but it's a good example for this to kind of help you remember. Carbon has 4, oxygen has 6 times 2. So that means I have 16 electrons available. Okay, so that's my budget. Okay. Now my test structure follows the certain characteristics: all single bonds, and any element with 4 or more valence electrons gets an octet. Okay, so any element in group 14 or higher always gets an octet in your test structure. Okay, and then your job is to kind of manipulate that structure to match your actual budget. This always works because it starts with a worst case scenario, and then you can change it to match your scenario. So that's why this works. Because the fewest bonds, the simplest bond you can have between two atoms is a single bond. So that's non-negotiable. And every element that has 4 more valence electrons needs to have 8 electrons total. That's also non-negotiable. At least 8, I should say. So if I'm drawing this, C is in the middle. Oxygens are on the outside. Again, this is my test structure, not the reality, but my test structure. The problem is here, though, when I look at this, there is 20 electrons drawn in here, which means there's 4 too many. Okay, which means I need to add bonds. Okay, and every bond, remember, equals 2 electrons that you're reducing from this, because instead of each oxygen having a lone pair and a carbon having a lone pair, they're actually sharing those electrons instead of having individual pairs. Okay, so in this case, I would need to add 2 bonds. And since they're both the same scenario, I would add them on one on each side. And I would eliminate these theoretical lone pairs to do that. Okay. Questions about how I did that? Yes, Alexandra. That's a good question. So what you're saying here in the test structure is you're assuming that every atom has its octet because it has its own lone pairs. But in reality, sometimes those lone pairs are actually shared so they both can claim that they have a pair of electrons. Like for example, okay, let's just say you and Virginia, let's say y'all share shoes, okay? Technically, y'all could both have 4 pairs of shoes and you could say that you own 4 pairs of shoes, okay? But you could each say you have 4 pairs of shoes if you each own 3 pairs and you shared 1 pair, right? Because you both could claim that shared pair of electrons. So what this diagram does is says, okay, let's assume the worst that you had to each buy 4 pairs of shoes. But in reality, you don't have 8 pairs of shoes at your house. You only have 7 pairs of shoes at your house, which means that 3 of them must be each of your own, and you must be sharing 1 so that that matches the number of pairs of shoes you have at your house. So that's what this is doing here. So what we thought were 2 lone pairs is actually a bond where both atoms can claim those electrons. Does that make sense? Okay. You're welcome. Yes. It's tricky. I've read things where they say like dots are really hard to see sometimes, and so they prefer lines for lone pairs. So I would stick with lines because I would hate for you to like have a dot not pick up on the scanner and stuff like that, and then they would dock you for that. So I think lines for lone pairs is much more foolproof. Okay. Well, although they do let you do dots and crosses. Well, if you're going to do that, just make sure it's very, very clear. Yeah. Okay. What's great about this is this works for resonance as well, because resonance isn't always obvious if you're just trying to pair up electrons with dots and stuff like that. And so what's great about this is you might see something like O3. Actually, you know what? Let me do CO3 2 minus. Okay. Because this incorporates a couple things. You need to add the charge into your budget as well in this. Okay. So we say, okay, carbon has 4. Each oxygen has 6. And we have to add 2 because the charge is negative, which means you gain 2 electrons in this. So that means you have 24 electrons or 12 pairs available in your structure. Okay, if you want to divide by 2 to make it easier to count instead of counting every individual electron, you can as well. Now my test structure. Because carbon and oxygen each have 4 or more, I need to draw it so that every one has an octet. But the problem is this is, oops, sorry, 13 pairs. So it can't be this structure because we have too many electrons in this. So we need to add a bond because we're supposed to get to 12. So 2 of these lone pairs are actually a bond that we don't see here yet. Okay. But the question is, where do you add the bond? Does it matter on which oxygen I add the bond on? No. What that tells you is there is resonance. So what that's telling you is if I have a bond I need to add and there's more than one location where it could exist and be the same, then you have resonance. So if you have to ask yourself, okay, where am I going to put this bond because they're all the same, that should trigger a thought that says this is resonance. Yes, Alexandra. No, by saying that you need to add one bond, but you have more than one location that's identical to add that bond, that's resonance. So you see here, I have 3 different locations that are exactly the same that I can add the bond. So there is no preference, which tells you that there's resonance. Okay. So if you're going to draw the resonance out for this, you actually have to draw, if they state it, you need to draw all 3 resonance structures. So you have to show how that double bond resonates around Oh, sorry. Thank you. So those are all the resonance structures possible. Do not draw dotted lines and stuff like that. That is, I don't believe, acceptable. You need to draw, if they ask you, draw all possible resonance structures, then you need to draw all three of these in this case, because that double bond could be in all three places. Now, is it, oh, sorry, I'll give you a second to write it down. Going too fast. Yeah. Like, I should just like start like in different topics, speak really, really fast for like 5 minutes and then slow down, and just to mess with y'all, make sure y'all keeping on top of things. I never said I was nice. Now, is there an actual double bond in this structure? Like, is there an actual double bond here? No, because it's kind of distributing all the way around. So what you're really looking at is 4 bonds in 3 locations. So the bond itself is effectively like 1.33 of a bond. We call that bond order, in case you may have heard that term before, but bond order kind of explains like what's the effective strength of a bond. So this bond, this CO bond here, is 1.33 of a bond. So it's more than a single, it's stronger than a single bond. It's weaker than a double bond. So it's kind of right in the middle. Not right in the middle, closer to a single, but you get the idea. How might you think experimentally that we could tell that there is resonance if we measured the bond lengths of this atom? How do we tell that there's resonance experimentally? Daphne? It should be shorter. So in this structure, what do we expect all the bond lengths to be? Well, sorry, let me clarify that. If this double bond existed, you're right, one of the bonds would be shorter than the others. But experimentally, we found that that's not the case. We find that all 3 are the same, which proves the existence of resonance, right? Because like Daphne said, if this was actually double bond and you measured the bond lengths, one would be shorter than the other 2. But in reality, when we measure the bond lengths, they're all the same, which means that this pair of electrons is actually rotating equally throughout all 3 regions. Sorry, I don't think I phrased that question very well. So that's proof that resonance exists, because those bond lengths are all the same. I'll write that down here. Bond lengths, all the same. Yes. Yes. Yeah. So for example, that's a good question. Let's say we have ozone. Okay, O3. Okay, that is 18 electrons or 9 pairs. If we draw our test structure out, we see that there are 10 pairs. So we have to eliminate 2 lone pairs and make a bond. The problem is they're the same. So you'd have to draw both this way and this way. And the bond order here would be what? 1.5, because it's 3 bonds per 2 locations. So this would be a 1.5 bond order. So yeah, just make sure you divide by the number of locations the bond can exist to help you figure out what the bond order is. And you can use that to support your answer if they ask you like which one's a longer bond length, which one is shorter. You can use bond order to do that. You can use that idea to support your concept. Like, so let's say, like I've seen this question on all exams. Like they'll say, compare the bond length of the C to O bond in CO2 versus CO3 2 minus. So you could say the bond length in CO2 is shorter because the bond order is 2, because there's 4 bonds for 2 locations, the bond order is 2, and the CO3 bond order is 1.33, which means this is a stronger bond, which means the bond length should be shorter. So you can use bond order to help you support your explanations for bond strength, bond length, etc. What's going on? Questions about that? Yeah, I would say I would just do your Lewis structures this way always, because I just think trying to memorize some Lewis structures with dots and then trying to memorize other structures that are exceptions, just have one uniform way to do all the structures. Yes, it may take longer sometimes, but it'll take shorter other times, and it ensures that you get the right structure every single time. Why not do it that way? Okay. You have to remember that I am lazy, and I'm only going to tell you the simplest way to do things from my experience. Okay. Unfortunately, I do have the mentality of a high schooler, so I know exactly how to make things stick with y'all and simplify things. Because I'm almost 40. Okay. Thank you. Appreciate it. I've almost taught as many years as 8 years y'all are old. I'm just thinking about this. This is my 15th year teaching. It's crazy. Okay. So, Lewis structures. Remember that and apply that for everything. Okay. Shapes. Okay. I know. This is a big minimize what you have to memorize. Yes. Yes, Cass. No. Sorry. Okay. Especially for higher level, because you're higher level. So yeah, no. I don't know, maybe. Okay. Here's what I want you to think about when I do shapes. Okay, minimize what you memorize, because instead of memorizing 15 or 9 shapes, or even like 6 shapes, you can simplify this by following my kind of sketches for this, okay? These are higher level, by the way. So SL, you're just the left 3. Let me make dots on here so I can kind of show y'all. Let's see. This dot, dot. I've come too far. I'm going to commit to them. Wow. Everyone's a critic. Okay. So here's what's great about this. Okay. The first thing, okay, these are what we call electronic geometry. So that means that no matter they're bonds or lone pairs, the electronic geometries are only 3 or 5 possible shapes for SL and HL respectively. So you can't have the whether they're lone pair or bond doesn't matter for electronic geometry. Where lone pairs matter is when you have molecular geometry, which is these 5 and then also the rest down as well. Okay. And the reason why I drew these shapes this way is because if you know these shapes, you can actually figure out all the other shapes based on these. Because what I do is I cover up different dots and then I can see what's left on the shape. Okay. So for example, this right here is linear. Obviously, it's a line. Okay. This is trigonal planar because it's a triangle that's flat on here. And this is tetrahedral. Tetra meaning four, hedral meaning faces. So this molecule has four different faces. When you connect the 3 points together, there's 4 different faces that are formed in 3D. Okay. But what's nice is if you start getting lone pairs, all you do is you remove the line, one line from the shape. Okay. So if you remove that line from the shape, what shape is left? Bent. Exactly. Okay. And we remove this line from it. What shape is this? Make sure you think in 3 dimensions. No, not seesaw. Pyramidal. Yeah. Oh, sorry, I heard another thing. Okay. Trigonal pyramidal. Seesaw, remember, you need to have the 2 legs and the 2 seats on the seesaw, which we're going to talk about at a higher level. Okay. And then you take this shape and then you remove one more. And what is this? Bent. So this is why I say minimize what you memorize. And so instead of memorizing 6 shapes for SL, if you memorize 3, you can figure out the other 3 shapes that are present here. Okay. Every little bit counts. Okay. So I think if you know these first 4 shapes and you draw them, you can actually reduce what you have to memorize. In HL, it's even more, because in HL you need to know what, like 13 or 14 shapes, and you only need to know 5 to start with. Okay. Oh, I should have moved this down to the next page myself. Oops. Okay, for higher level. Okay, this one's a little bit harder to see, so you do kind of memorize this, but this is trigonal bipyramidal. You want to think of it as a pyramid that comes. Oh, that's probably not the best way to draw it, but it's 2 pyramids that come to a point in that middle here, because it's 3 dimensions. Okay. Now I draw it this way on purpose because I want to take the top one off every single time. Okay. Okay. So what is this shape? This is seesaw. Or sawhorse, depending on your review notes. Okay. Now, this is where it gets a little more complicated, because when you start taking away from here, it actually matters where you take away from, because they're not all the same. Which of these dots that's left over is furthest away from the original dot you took away? Yeah. One's the one on the bottom. So we're going to take away one of those. Because remember, lone pairs want to be as far away from each other as possible. So if you're going to start taking away lines, you want to take away lines that are furthest from each other as possible. Yes, for everything. It just really matters more in HL than SL. In SL, you don't have that many options, so no matter where you take it from, you'll get the same shape. Okay. You want to take a guess what this shape is? T-shaped. Really went out on a limb there. See, for every meth, eth, bute, and like meth, eth, pro, butane organic naming, there is some naming in chemistry that's very intuitive. Okay. Now, which dot is the furthest away from the dots you took away? It's also this next one as well. So you just take away the y piece by piece and you end up with linear. And that's the extent of that for HL. For 5. This one is octahedral. okay? I know it's 6, but you want to think of it as X, Y, and Z, and each of those 3 points makes actually 8 faces. That's why it's called octahedral. Okay? So I'm going to take the top one off first. Okay. Now, what shape is that? Remember those first 4 are flat and the bottom one's pointing down. Okay. Can anyone see what shape that is?
A cone with like a square base.
Square base with a kind of, yeah. What do we call a cone with a square base? A pyramid.
Exactly, I knew that, obviously.
Yes, that's why you said cone. Okay, so square, pyramidal. I have to remember I'm recording. This is all evidence that can be used against me. Perrin, you're a wonderful and smart student. I appreciate your attempt at answering that question.
Thank you, Mr. Chong. You are my favorite teacher.
So we're both telling lies now, Perrin, huh?
Exactly.
The one where you said that Alexander was the bond mode of next to you, like on.
Oh yeah, that's true. I'm just glad I don't record y'all's class minutes because there are some things that I say in that class that.
You get quoted in that class.
Yeah. Well, they're just gonna laugh. Okay. Now, where's the next dot we take away from if we're trying to take the first dot away from where we originally took away from? The bottom. So we erase that one. Okay. No. You took away the point of the pyramid. What's left? A square. Okay. Now it's flat, so it's square planar. Okay. It does look kind of like an X, but you can make an X into a square if you connect the ends of the X to each other. Okay. The next one, now that they're all 4 the same, it doesn't matter where you take from. You could take away from here. Okay. And what shape is that? Nope. T-shape. Seesaw needs 2 legs, remember? Yeah. So T-shaped. And then you take away the next one that's furthest away from the one you just took. And then you're back to linear. Okay. So see how many shapes that you're actually reducing by memorizing these 5 shapes. Because HL, you have to know 15 shapes. Okay. But if you know those first 5, you can slowly. Yeah, I lost my stapler yesterday. I'm like, oh man, some kid's gonna take it. So I'm glad I was. Thank y'all, man. So again, minimize what you have to memorize. If you memorize these 5 shapes, you can figure out all these other shapes when necessary by taking away lines from your shape. What are you looking for, Marcel?
I'm just like.
Oh, quite a few topics. Now, for HL as well, you want to think about hybridization. Okay. Hybridization for HL. Okay. Now, here's what's good about hybridization. Hybridization is based only on the electronic geometry, not the molecular geometry. So all these structures have the same hybridization, and all these structures on the right have the same hybridization. So it doesn't matter whether you have lone pairs or not, they all have the same hybridization. And what you want to focus on is how many hybrid orbitals you need, which is the number of dots on the structure. Okay, so here you need 2 hybrid orbitals. So you're going to hybridize one s and one p. Here you need 3 hybrid orbitals. So it's sp2. If you have 4 orbitals that you need to hybridize, what do you think that is? sp3. Okay. 5 hybrid orbitals. There is no 4 p's. So what orbital, what d? So it's sp3d1. So you do want to remember that there's only 3 p orbitals, because that means when you do expanded octet, you have to use d orbitals to fulfill that hybridization. And here it's sp3d2. Okay. No, you don't have to write the 1. Yes, Cass. Oh, it tells you how many orbitals in that sublevel you need to hybridize. So sp1 is 1s and 1p that hybridize into 2 new orbitals. sp2 is 1s, 2p make 3 new hybrid orbitals. So you need the same number of atomic orbitals to make the same number of hybrid orbitals. Yep, exactly. So if someone tells you the hybridization is sp3, that tells you you've got 4 dots, which means you have a tetrahedral electronic geometry. Okay. Now, HL, you still need to know some bond angles here. So 180 with linear is pretty self-explanatory. 120 here is also pretty self-explanatory. And 109.5 or 110 for tetrahedral. Right? And if you want to know the angles of the next ones, it gets slightly smaller for every lone pair. So this becomes 117, this becomes 107, and this becomes 104.5. Oh, in between. That's a good question. Bond angle is always between the atoms. Thank you. Because that's a good question. The lone pair that's present causes more repulsion and pushes the atoms closer together. Now for HL, you just need to know that this has 120 and 90. And all of these are 90 because X, Y, and Z essentially. You don't need to know the bond angles specifically for the other ones. Questions about that? 90? Yeah. Questions about anything? Oh, yes. Yeah.
Do you mind repeating what the highlighted part is?
Oh, I highlighted to tell you that all those shapes in that column, Perrin, are the same hybridization.
Okay.
So like any of those shapes, you would say is sp3d2, sp3d1. And all of these shapes here would be sp3d2.
Thank you.
You're welcome. Yes, Alexandra. Sure. Electronic geometry doesn't differentiate between bonds and lone pairs. So for example, if you look at water, water has 2 lone pairs and 2 bonds. So you'd have an electronic geometry that's around 4 dots. because each lone pair counts as a dot and each atom counts as a dot. So it would be tetrahedral electronic geometry. But when you talk about molecular geometry, you only care about the atoms. So then you start removing the dots that are lone pairs and you only talk about the atoms. And when you look at water, because there's two lone pairs, you take away two of those dots and you end up with a bent electronic geometry. Molecular geometry. So electronic are the first five. Doesn't matter whether lone pairs or atoms, you count them each as one thing. But then when they ask for molecular geometry, you start taking away dots that are lone pairs. And also remember, a double bond is the same as a single bond when it comes to like number of dots. Or a triple bond is the same as a single bond because you're still just making one connection to an atom. Yes. 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 Correct. Yes. Oh, well, the arrows in the orbital diagram represent electrons themselves. And so the thing is, let's see, let me make sure I'm answering your question correctly. You're asking why are there two different representations for free radicals? Or? They're not. Wait, what do you mean? Yes, correct. Oh, that's just because in the context. So in the context of orbital diagrams, every electron is an arrow. So that's why they're represented as arrows there. But when you're talking about Lewis structures, everything's represented by a dot. So that's why we draw a dot in a balanced chemical equation, we draw it as a dot, just to represent that one electron that's there. I think I see what you're saying. Okay. All right. Other questions? Okay. We'll do topic 5 and 15 for HL, and then we'll take probably like a 10-minute break because it's a lot of information. Okay. Topic 5, SL, is enthalpy, delta H. Okay. And we're not going to go over all delta H and stuff like that, but I want you to think about this, okay? There are some times you have to memorize whether you're doing products minus reactants or reactants minus products. And I don't want you to memorize that, but I do want you to understand how to figure out whether it's which one is which, okay? So don't memorize products minus reactants, but if you know this information, you can tell which one it is, okay? So there's 3 different ways you can really solve for delta H, other than calorimetry, which is its own kind of beast. The first one is enthalpy of formation. Okay. And I'm going to do it like this. I'm going to write a general equation up here for us to use for all these applications. Okay. Yes, that's electrophilic addition of an alkene. Sorry to bring back bad memories. Okay. Now, enthalpy of formation, you need to know is elements forming the species. And so, for example, the enthalpy of formation of C2H4 is 2C solid plus 2H2 gas yields C2H4. That's what the enthalpy of formation represents. That would be your delta H of that. We'll call that delta HA. Now here, H2 is an element. So that has a delta H of 0. Because, sorry? Yeah. So the enthalpy of formation of H2 is 0 because all elements have enthalpy of formation 0. That's our baseline for the energy, inherent energy in every atom. For C2H6, it's this. And everything is a Hess's law problem, okay? So if you know the enthalpy of formation definition, and you can write one of your enthalpy of formations out, what you can see is this, okay? All the reactants in your overall equation are on the wrong side of enthalpy of formation. Do y'all see that? Which means all of the reactants need to be reversed, okay? So that means all the reactants are negative the value of that reactant. All the products are on the correct side. So you don't have to reverse them. And this is why it's products minus reactants for enthalpy of formation. Yes, Marissa? Oh, yes. I was just putting a placeholder for the delta H values.
Oh, okay.
Yeah.
They're just delta H.
Yes, correct. Sorry. I should have said delta H equals A, delta H equals C. Okay, yeah. Let me change that to avoid confusion. Yeah, I shouldn't have labeled that way because it makes it look like it's a subscript that means something. So this would be delta HF is equal to A, delta HF equals to B, or C, I guess. Okay, and so in this problem, it would be C minus A. Now, if you have coefficients, yes, you have to multiply the reaction by that, but the main thing that students forget is it products minus reactants or reactants minus products? And if you do it this way, you solve two problems. One, you remember the definition of enthalpy of formation, which is something you need to know. And two, you can come up with the products minus reactants without having to memorize it. Because again, this is one of those things where if you try to memorize it, it's a coin flip whether you get it right or wrong. And if you don't understand whether it's right or wrong, then you're just gambling on points by just flipping a coin. But if you understand Hess's law and understand what the enthalpy of formation is, you don't have to coin flip. You will always be able to figure out that it's products minus reactants. Okay. Again, that's why we focus on kind of understanding a lot of these concepts, because I don't trust my memory, and I don't think you should trust your memory when it comes to those kind of things. Okay. It's very easy to get these things backwards. And if you don't understand why it's backwards, then there's no way that you can kind of check your answers and prevent mistakes. Yes, Alexandra. Correct. Because enthalpy of formation is always of one substance every time. So you look at where that substance is located on the overall reaction, and it's on the wrong side, so you have to flip the sign of that value. Yes. So if you do that for one of the reactants, you'll know, oh, all the reactants are negative because they're on the wrong side. So then it's products minus reactants. You're welcome. With combustion, let's use the same reaction here. Okay. Enthalpy of combustion is combusting each of these substances with oxygen to form CO2 and H2O. And elements also can combust. Oops. You also write that down. Again, if you forget all this, or not forget all this, but if you want to write all the reactions out using Hess's law problem, that's fine. It may take you another minute or so, but you can still do it. If you're not sure, you can write them all as Hess's law and then just solve for them accordingly. You won't run out of time doing that. So what do you notice about the values of enthalpy of combustion and what they're talking about here? C2H4 is on the correct side now, okay? And H2 is on the correct side. What's reversed is C2H6, the product. So in this case, it's reactants minus products. So it's A plus B minus C. Or if you want to think about it as A plus B plus a negative C, that's fine too. If you want to really think of it as Hess law, it's the same thing. So again, instead of memorizing products minus reactants, reactants minus products, think about the definition of the type of delta H you're using and find out where the substances are in that reaction, and then that will tell you whether it's reactants minus products or products minus reactants. So that way you can kind of justify your reasoning instead of just hoping that you remembered it correctly. It's very easy to get things backwards on this stuff. And you're losing points that you shouldn't really be losing. Questions on that? Topic 15. Gives free energy and entropy. So this is higher level. The only thing I'm going to talk to you about in this section is really this equation right here. Delta G is equal to delta H minus T delta S. That's the important equation in topic 15. And what's important about that is if you're given the signs of delta H and delta S, you should be able to determine whether the reaction is spontaneous or not. So again, this is something to minimize what you have to memorize. Know this equation, and then if you know the signs, then you can figure out whether it's spontaneous or not. And so I break this down like this. And there's 4 possible combinations of signs you could have. You could have negative delta H or positive delta H. And you could have negative T times negative delta S, negative T times positive delta S, negative T times positive delta S, and negative T times negative delta S. Those are your 4 combinations of terms. Okay. Again, don't memorize this table. I'm telling you, do not memorize this table because you should be able to logic and understand signs well enough to be able to figure this stuff out without having to memorize this. Don't memorize 12 pieces of information when you just use this, and whatever one problem they ask you, you can just plug in signs and figure it out. Okay? So for example, row number 2 here, okay? Negative delta H minus positive delta S, okay? What will the sign of delta G be in the second row here? It will always be negative. Because you have a negative delta H plus a negative T times positive delta S, which is also a negative term. So negative plus a negative is always going to be negative. What about this bottom one? Positive delta H minus T times negative delta S. It's always positive. So this is never spontaneous. because delta G is always greater than 0. No matter what you do, because temperature can't be negative, by the way. Temperature cannot be negative because it's in Kelvin. So the only signs that matter are delta H and delta S. Okay. Now the top one, negative delta H plus a negative T times negative delta S. Okay. What term is this dependent on? Because you could get a positive or a negative value here. Okay. So what does it depend on? Let me rephrase that. Yeah, temperature. Yeah, temperature. Because here, negative T times negative delta S is what? Positive. So if you want a negative delta G, what kind of temperature do you want here? A low. Because temperature's hurting you here. Y'all see that? Because this is a positive value, so that's hurting your negative delta G. So here you want a low temperature. Because T, the larger T gets, the more positive it gets. Okay. On the third one, though, you have a positive delta H and a negative T times positive delta S. So temperature is now helping your value here. So you want a high temperature here. Because again, this is all algebra. Yes, Alexander. Because that's the definition of spontaneous. So a reaction is spontaneous when delta G is less than 0. So if I give you the sign of delta H and the sign of delta S, you can tell me, generally speaking, when the reaction is spontaneous. If it's negative and a positive, then you always get a negative number, so it's always spontaneous. If you get a positive delta H and negative delta S, because this negatives cancel out, they'll never be positive, negative. And then these two depend on the temperature, because that's the one term that influences which of these values is more important. So again, don't memorize this whole chart. Just be able to plug in a negative and positive and figure it out when necessary. This is just one of those huge examples of don't memorize 12 pieces of information when you only need one. Because I'm telling you this right now, kids that try to memorize this, they're bound to get one of these wrong. And if you get one of them wrong, you'll never know. Questions? Let's take about a 5 to 7 minute break right here. Let y'all kind of stretch your legs, use the restroom, or get some water and stuff like that. And then we'll come back and kind of get through topics 6, 7, 8, and 9, and 10 respectively. Y'all did 6, y'all didn't do 16. 6 is factors that affect the rate of reaction and things like that. Y'all did that last year.
No, but I mean integral.
No, we have not. Yeah. But 6 itself isn't super like complicated. And so I'm going to kind of go over the main idea of 6 that I really want you to take away from this. And so topic 6, SL. Rate of reaction. Okay. So to kind of simplify things down, collision theory is what all of this is about. Okay. And there's 2 factors that determine whether a reaction will occur or not. So a reaction occurs when 2 species collide, and so you have to have only 2 species colliding, and 2 requirements have to be met. 1, the correct amount of energy, which we know as activation energy, and the correct orientation. And so everything that affects the rate of reaction affects one or both of these things. And that's what you want to think about. So you have to collide the correct way, and you have to have the right amount of energy in that collision for the reaction to occur. Things that affect correct orientation. Okay. Surface area. Okay. The more surface area you have, the more successful collisions you have, because the more opportunities for the correct orientation is possible. 2, concentration. Okay. The more particles you have, the more collisions you have, therefore the more successful collisions you have. It's just a game of numbers at that point. Okay. Pressure for gases, right? The more pressure you have, the more you're forcing gas particles to collide, the more correct orientation is possible. And temperature. Okay. The faster the particles are moving, the more quickly that they'll collide with each other, and therefore more possible correct orientation. So you're really just increasing the collisions here. That's what you're doing with these ideas, is you're increasing the number of collisions. That's how you get more successful orientation. You're not necessarily changing the energy of the particles. You're not necessarily making more of the collisions successful. You're just making the fact that you have more collisions, therefore by default you'll have more successful ones. It's like saying, like, out of every 100 people, 5 people are redheads. Well, if you have 1,000 people, then you have 50 redheads, right? It's a game of numbers. If you have 100 collisions and 5 are successful, if you have 1,000 collisions, 50 are successful. So it's all about a game of numbers there. Oh, let me write correct energy. Okay. There's only 2 factors that affect correct energy. 1, temperature, because correct energy is the speed of the particles. So surface area, concentration, that doesn't affect the speed of the particles. That just affects the number of collisions. But temperature, as you increase temperature, you're giving the particles more energy, so they're moving more quickly. So they collide with more energy each time. Okay. And a catalyst, which lowers the activation energy. So a catalyst doesn't speed up the particles, it lowers the requirement for those particles to react. So everything can be explained with either orientation or successful collisions or amount of energy. Yes, Alexandra. Oh, the fact that you just have more particles in the environment means there's going to be more collisions, right? A higher molarity, that means more moles of particles, which means more collisions by default. Okay. Now, for temperature, this is more important, the correct energy. So while they both increase the number of collisions and you get more energy, the more energy is more important, because you can have more collisions and not have enough energy for all those collisions, and then they still won't be successful. But when you make more particles have the right amount of energy, you can increase the number of successful collisions with the right amount of energy. I think I just talked myself in a circle right there. Okay. Thanks, Marissa. I could tell, like, by Marissa's glare at me right now. So if your temperature is too low, even if you have more collisions by increasing it a little bit, the fact that you're increasing it and giving each particle more energy increases the chance of a collision with the right amount of energy, which is much more important than the number of collisions total. Okay. Questions about that? Now, there are a couple of diagrams that you need to know for this. One is the maximal Boltzmann curve. I would make this kind of big. Not like a whole page big, but you're gonna write some stuff on here. Maybe 10 to 15 lines. How many lines do you have on your page? Yeah, that's probably plenty. Okay. The Maxwell-Boltzmann curve is a distribution of particles in a sample, okay? And so here, this y-axis is number of particles with that specific energy. So this is kind of like a bell curve distribution almost. So the y-axis is number of particles with that specific energy, and the x-axis is energy, or sometimes you'll see speed because they're directly related to each other. Okay. Now this distribution looks something like this. It goes curves up, curves down, and then kind of approaches the x-axis here. This is the example of one distribution of particles at one given temperature. We'll call this T1. Okay. Now, if that's the distribution of particles at a certain temperature, if we heat that substance up, okay, what do you think happens to the shape of this curve? What happens to how this curve looks like if I heat up the particles and increase the temperature? Y left. Okay, so let's talk about that here. Okay, this curve is representing the temperature with the average kinetic energy of it being the peak. Okay, let's pretend. Let me give you an analogy here to think about it. Okay, let's think about traffic, cars on a highway. Okay, let's pretend this graph is the speed of the cars on the highway. Okay, now that peak is kind of the average speed of the cars on the highway. Okay, now let's pretend that the average speed of the cars increases. So from like 55 to 65. Now, how does your curve shift to reflect that there are more cars going faster? Y left. This is not time on the bottom. This is energy, speed. You have the same number, let's pretend you have the same number of cars, Daphne, but you have higher energy. So how does this curve change to show that the average speed of the cars is going faster? It'll stretch right. Because when cars speed up, you increase the range of speeds that the cars can go. Because now you've got more cars going faster, so the number of cars with a certain speed is shifting upward. It's trending upward here. Okay. So the speed of the cars is trending toward the right because more and more cars are going faster and faster. That's why your average is getting higher and higher. Yeah, so the thing is though, when you stretch the curve, you have to stretch the same number of particles out across a wider range. So the curve won't be as tall because they're distributed more and more across a wider range. Yes, because you need to think that the area under the curve is the total number of particles. Okay, so area under curve So area under curve is total particles. So the size of the shape, the size of the area of the curve should be relatively the same. So if you're going to stretch it, you have to make it wider and less tall. So T2 is greater than T1 here. Let me remove that. T2 is greater than T1 here. Now, let's pretend there was an accident on the freeway and it kind of slows down the traffic. Okay. Now, the range of the speeds that you can go on the highway has decreased. So if the range is decreased, then bless you, then how is the peak going to change here? It's going to be higher, but it's going to be to the left. Right, exactly. So you're going to see this. Oh, gosh. Peak high. And then approach down here where T3 is less than T1 because the lower the energy of the whole system, the more the particles are more like each other because there's less possible speeds for them. So there's going to be more going at the same speed. Do y'all recognize this curve from last year? Okay. A little, it's okay. I think you want to kind of approach the x-axis here. Yeah. Yeah, I guess there's theoretically like one particle that could be kind of like toward infinity speed, theoretically. Yes. So the original is kind of your baseline, and you should try to make the area of the curve relatively the same. So if you're going to make it colder, you need to make it taller, but also to the left. If you're going to make it hotter, you make it wider, but also shorter. They're not going to actually calculate the area of your curves, but it needs to be looked close. So you should never have the peak be the same height if you have a different temperature, because then there's no possible way the area is the same if your peak is the same. So like that's how they grade it. They say, is student's peak shifted to the right and also lower than the original peak for higher temperature? Or is the peak shifted to the left but taller for a colder temperature? Okay. Now, yeah, bye, Corinne. There is one other arbitrary value on here. And that's the activation energy. Okay, this is just a vertical line anywhere. Like there's not a specific place that goes on here, but what that means is all of these particles past this line have the right amount of energy to react. So notice this also reaffirms the idea that when you increase temperature, more particles have the right amount of energy to react, because if you notice the area of the red is much greater than the area of the gray or the blue. So this again reaffirms the idea that higher temperature means more particles have the right amount of energy to react. More particles have the right amount of energy to react, shown by the area of the curve that's past that line. Okay. Now, how would I show a catalyst on this curve? Yes, Marissa. Earlier, so meaning which direction? Relative to this one. Left, yeah. So this would be the activation energy of a catalyst. Because now you've included more particles because you've decreased the requirement of energy needed for the reaction to occur. That's why it happens faster. So yeah, understand a Maxwell-Boltzmann curve. Questions about this diagram? Yes, Alexander. No, it includes the stuff afterwards as well. I was just highlighting the additional area that's included now. So yes, you're right. It technically includes everything past the original point as well, but I was just showing the difference in area by highlighting that part. Okay. Questions? Okay, we're gonna skip 16 for now, and we're going to go to topic 7, equilibrium. Oh my, sorry, 105. Maybe we will go to 2. Sorry. Okay. 2 ideas from equilibrium that I want you to think about. Okay. 1. Q the reaction quotient. Okay. This tells you which way the reaction needs to shift to reach equilibrium. So Q might be greater than K, Q might be less than K, Q might be equal to K. And what you need to remember is that the main idea of equilibrium is products over reactants. Whether it's Q or K, it's products over reactants. So if Q is greater than K, you have too much products because your ratio is too high. So it shifts to the reactants. Oh, let me write reactants so it's not confusing. Because I could definitely understand why you see R and think right. K is the equilibrium constant. So K tells you at equilibrium which side of the reaction is favored. Which side is favored, like which one's in higher concentration. Okay. If Q is less than K, you have too much reactants. So keep in mind this fraction, because I'm trying to write this out, but you don't need to memorize all this, because if you understand the ratio of products over reactants, you can logic it out based on your need. Shifts to the products. And if Q is equal to K, you're at equilibrium. So the way you minimize what you memorize here is just remember that Q and K are both products over reactants. Q can change, K can't. So when you think about that, you can just make up numbers and plug it in there to represent your problem and see which way do I need to shift. Do I have too much numerator? Do I have too much denominator? And then shift to make those values match. That's the way you want to think about that. They're both fractions. You want to shift the values to make the fractions match. The second thing in this topic is Le Chatelier's principle. Okay. So this is where the reaction shifts to compensate for a change in its disruption of its equilibrium. Okay. And I'm going to write a generic reaction out here so you can kind of apply to it. Okay. The thing about Le Chatelier's principle is it requires you to have some knowledge of other topics. One, you have to understand what the sign of delta H means, whether it's exothermic or endothermic. Two, you have to understand state symbols. Three, you have to understand which way things are going to shift here as well. And that's, I guess, more topic 7. Okay. So if I'm trying to simplify this for myself, I'm going to include delta H into my reaction, okay? And if I were to include that value into my reaction, which side would I write the 100 kilojoules on? Which side of the reaction would I write the 100 kilojoules on? Products Y. Wait, what? It's being produced. Why is it being produced, Marissa? It's negative, okay? Because whenever you have delta H written outside of the reaction, the sign gives you context. And if it's negative, that means the reactants are losing that energy, and so therefore the energy is being produced on the product side. So you should think negative means exothermic, which means it goes on the right. Because once you establish that, everything is just shifting to return back to equilibrium, okay? You might have something like increase A. If I increase A, what's going to happen to my equilibrium? Which way does it have to shift to restore back to it? Yes, Alexandra. Why? Exactly. You have too many reactants. You have to shift to the right so that your B will increase and your heat will also increase as well. Because you're trying to balance out the scenario. If you decrease A, which way does it have to shift? Left. Because you have to make up for the lost amount of it. So if you remove some reactant, you're going to have to make up for that by shifting it toward the left. Sometimes I think of this like, if you're a very visual learner, what I do is I'll use my pen or pencil and think of this like a scale, okay? Equilibrium is this is perfectly balanced. The reactants on one side, the products on the other side, okay? If the reactants are increased, this tips in favor of the reactants. And which way is it going to have to shift to return to balance? It has to shift to the products to restore this balance, right? So if you increase the reactants, it's got to shift to the products to restore that balance. If you decrease the reactants, it goes up. So now you have to shift toward the reactants to bring it back down to level, okay? And so that's one of the kind of big concepts here, okay? So you want to think of it as a balance. Oh, let me change colors here. So no, not that color. You want to think of it as a balance of A and 2B here. And that's your equilibrium. Now, in this case, if I increase pressure, which side is pressure going to affect more? Oh, yeah, let me rephrase that. Okay. If I increase pressure, which side of the reaction will, I guess I want to say affected, like which side of the reaction will be more affected by the increase in pressure? The one that has the most moles. Yeah, you have more moles of gas, but it's going to shift to the left because you want to shift to the side with less gas molecules. So an increase in pressure affects this side more because there's 2 moles of gas on this side and there's only 1 mole of gas on this side. So you want to go toward the side where there's less moles of gas. So you do want to shift toward the side with less moles of gas when you increase pressure. That's not always reactant, so you do need to count the number of moles of gas you have in each problem. And if they're the same amount of gas, then it doesn't matter. There's no effect. Okay. Now, with these ideas, I want you to make a note that K stays the same. Because everything that's affecting the balance in these factors is held within the balance. all the reactants and products are on the scale, the balance scale. So whenever you shift it, they can restore the same result by shifting things left and right. Okay. The problem is temperature is not on that scale. Temperature is an additional factor that's affecting the scale that's not included in the K expression. So temperature would be like someone standing away from the scale and pressing their finger down on the scale or lifting the scale up to cause an imbalance. And when that happens, your K actually does change. Okay. Now, increase in temperature means increase in heat. And so which side is heat present in this reaction? On the right. So if you increase heat, which way is it going to shift? Left. So you're going to increase reactants and decrease products. And what's going to happen to K now? Because you have more reactants and less products, what's going to happen to K? It's going to get smaller. It's decreasing. I like how Alexandra said the first part of the answer and then stopped and made sure I said it right so that she wouldn't get it wrong. She's like, what was the question again? Nice recovery, Alexandra. So if heat is on the right, when you increase temperature, your K should decrease because you're going to be making more reactants and less products. If you decrease temperature, then I'll shift this way, so K will increase. So temperature upsets the balance, but upsets a factor that's not expressed in K. That's why K changes. Because K is just products over reactants. Heat is nowhere in there, so heat can't restore back the same balance in the ratio as A and B could. And again, I don't want you to memorize, oh, if it's exothermic, when temperature goes up, K goes down. Or if it's endothermic, temperature goes up, K goes up. Think of it in Le Chatelier's principle manner and just apply that and test it out yourself. Like what would happen if heat was on the left or heat was on the right, and just figure that out instead of trying to memorize these minute details. Because again, if you memorize it wrong and you just write that down, there's no way to check your logic because you don't understand what you're memorizing. And so that's how it's really easy to get it backwards. Yes, Alexandra. Generally speaking, yes. If you increase something for Le Chatelier's, it goes away from that increase. Yes. If you decrease something, it goes toward that decrease. Yes. That is a simplification of this. Yes. If you have a catalyst, what is its effect on equilibrium? Nothing. It just helps it get there faster, but it doesn't affect how much a reactant or product that you will get. So that's a big one here. No effect on catalyst. And no effect on K either. Questions on that? Okay. Okay. Topic 17, there's really nothing that you can minimize what you have to memorize because really topic 17 is just Rice charts and delta G is equal to negative RT ln K. And so with this, you're just kind of showing the relationship between K and delta G. And you want K to be greater than 1 so that this whole thing becomes negative. Because if natural log of k is greater, if k is greater than 1, then the natural log is positive, r and t are positive, so then therefore delta g is negative. So you want a k greater than 1 if you want a spontaneous reaction. So again, you don't need to memorize that equation that's given to you in the data booklet, but you can just apply that concept without having to memorize it. Okay. Things that I would take away from topic 8 here. What would I minimize with that to memorize here? Okay. The foundation for all of this topic really is what strength means. Okay. So whether it's a strong acid, strong base, weak acid, or weak base, things like that, that's the main idea. So when you say something is strong, that means it dissociates 100%. And when you say something is weak, it dissociates less than like about 1% or partially dissociates. Okay. And every property of a strong versus a weak acid or base is dependent on that, whether it's conductivity, pH, reaction rate. Okay. And this all needs to be equimolar, by the way, the same molarity, because you can only compare them when they're the same molarity. But so these properties of each solution are dependent on how much is it ionized, because the more ions you have, the more conductive it is. The more ions of H plus or OH minus you have, the stronger the pH is. The more ions you have, the faster the reaction rate will occur. Yes, Alexander.
Would the IU like on purpose not say that they're equimolar?
No, they would not try to trick you. Like, they would generally say, comparing an unknown strong acid versus a weak unknown weak acid that are equimolar solutions, state one technique to differentiate them. So no, that I don't believe that that's something they do. So I want you to kind of focus on that concept here for strong and weak, because that's what it all comes down to here. pH scale, that's the other thing here, okay? Remember, pH is equal to negative log of H plus. In fact, P of anything is equal to the negative log of that. So whether it's pH, pOH, pKa, pKb, pKw, it's always negative log, which means you can rearrange this into 10 to the negative px is equal to the concentration of x. Okay. So again, minimize what you have to memorize, because if you know this equation, you can undo that equation to figure out the reverse. And also know that pH is on a scale of base 10. So every 1 unit of pH is 10 times the difference in molarity, whether it's 1/10 or 1/100th or 10 or 100 times based on the value of pH. Questions about that? Okay. Topic 18, HL. Okay, there's two things that I want you to take from this to try to minimize what you have to memorize. Okay. One is pH of salts. Okay. Predicting the pH of salts is based on the original acid and base strength. So you should know how to determine the acid and base from a salt by just looking at it, okay? The trick is this. I generally, if I see a metal and non-metal, the second half is always the acid, and the first half always came from the base. So what acid did this come from? Acid.
No,
HCl, sorry, you got the other thing. It's NaOH. Right. So you have your base and you have your acid. Now, this is a strong base and this is a strong acid. So that means it's neutral. But if I have something like this, NH4 came from NH3 and NO3 came from HNO3. This is a strong acid and this is a weak base. So therefore this is acidic because the stronger part of the original parent, original acid and base dictates the pH of the salt. So if you see it came from a strong acid and a weak base, it's acidic. If it comes from a strong base and a strong acid, it's neutral. If it comes from a strong base and a weak acid, then it's basic. So identifying the original original acid and base is really important for you to kind of simplify this. Okay. Buffers. Okay, I know that word kind of strikes fear in your hearts already. Okay. Here's what you should think about when you're trying to determine whether something's a buffer or not. Okay. One. Wait. Okay. Is it a weak conjugate acid base pair? Okay. Because if the buffer is, then you already know it's a buffer. Okay. If not, then can you make the conjugate with leftover weak? Okay. So this is making buffers. So can you react the two substances that you're given, Alexandra, and then still have leftover weak acid or base when they react together? Because the whole point of a buffer is to have a weak acid and a weak base that can absorb H plus to make the weak base, or it can absorb OH minus to make the weak acid. That's why a buffer works, because you're making each other. You're making a conjugate acid base pair in buffer action. So the whole point is, can you react with an addition of H plus or OH minus to make the conjugate of itself? And so when you think about this, something like this, if you see something like NH3 and NH4Cl, okay, you know NH3 is a weak base, okay? Well, if NH3 acts as a weak base, what do bases do? What do bases do? Gain a hydrogen, an H plus. So what would the conjugate acid of NH3 be? NH4 plus. Do we have NH4 plus? It's a buffer. That would be the first question, right, Alexandra? Do we have the weak base and its conjugate acid, or do we have a weak acid and its conjugate base? Yes, so this is a buffer. Because the NH3 can react with any added H plus to form NH4 plus. NH4 plus can react with any OH minus to form NH3 and H2O. So notice how they work in tandem to make each other to absorb any H plus or OH minus in the solution. That's how that works. But for question 2, you might get something like HF and NaOH. Okay. If HF reacts with NaOH, what do you get for your products here? If HF reacts with NaOH, what do you get for the products here? H2O and NaF. Notice NaF is the conjugate base of your original weak acid. So when you react the NaOH with HF, you can make some of the conjugate base that you need for your buffer. But what do you have to be careful about? That you don't run out of HF, right, Marissa? So the amount of NaOH needs to be less than the HF so that it can become a buffer. So the moles of NaOH has to be less than the moles of HF that are needed to react with it. So you still have some HF and you still have some NaF to make a buffer. So be careful about that. I don't think they try to trick you on multiple choice by like making a reaction that needs to be balanced. On multiple choice, they probably just have you do a 1-to-1, so it should be obvious. But just be careful. Sure. Remember, a buffer has to have the weak acid and its conjugate base in there. If you add too much NaOH, you'll react all the HF away, and then it won't be a buffer anymore. You want to react just enough so that you make some NaF, but you still have some HF left over, so these two things can act as a buffer together. That would be you calculating the moles of each that you need. So for example, oh, ouch. Okay. Yeah, I'm good. I don't need the left leg anyways. Okay. All right. What they would probably do here, Alexander, is they give you the molarity and the volume of each substance. Okay. So let's say I gave you 100 centimeters cubed of 1.0 molar HF and 50 centimeters cubed of 1.0 molar NaOH. Okay. Now, these react 1-to-1, right, Alexandra? Okay. So if the molarity is the same, then that doesn't really matter. It's the volume of it that you need for each of them, right? And because you have less volume of NaOH, this could be a buffer. Okay. Now, if this were 2 NaOH, then you'd need to have less than half the volume. So like, that's kind of the tricky part, because like what you might have is like this. And then if H2SO4 isn't a weak acid, but I'm just kind of showing the point here. If I have this, This is not a buffer because 50 of this reacts with 100 of this because of the molar ratio. Actually, no, that's backwards. Sorry, it's backwards. Wait, no. No, I had that backwards. I'm sorry. Yeah, because I need twice as much NaOH there. That's my fault. So 100 of this reacts with 50 of this. So all of it would go away, so therefore you couldn't have a buffer, disregarding the fact that H2SO4 is a strong acid. I could just make it H2SO3, to be honest with you. That's a weak acid. So pay attention to the molarity, the volumes, if the molar ratio isn't 1-to-1. You have to really be careful. So like, for example, here, this could be 90 and it'd be okay, Alexandra. Because it's 2-to-1, that means I'd only react with 45 centimeters cubed of the acid, so I'd still have some left over. So don't let the volume right away dissuade you from answers. Yeah, buffers is kind of a tough thing, and we'll probably spend some time reviewing that a lot in April. Okay. Topic 9, back to SL. What do you minimize to memorize in this topic? Because this is electrochemistry. Oh, sorry. That's, yeah, voltaic and electrolytic cells. So I'm trying to figure out where you'd minimize what you have to memorize though, because because if you're diagramming this out, you're gonna have a lot, like, is there a lot to minimize what you have to memorize here? Yes, I will go over that. I think one of the things that I want you to think about is generally in oxidation, the electrons are on the right. So in an oxidation half reaction, the electrons are produced on the right side. And in a reduction reaction, they are on the left side. Okay. This is important when you're balancing half reactions because you want to make sure what's oxidizing, what's reducing, and the fact that you have electrons on each side of your half reactions. Because if you have electrons on both the same side, you did something wrong. So do keep in mind that oxidation means the electrons are on the right. Reduction means the electrons are on the reactant side or the left. Okay. Activity series. Okay. Activity series tells you whether a species can replace another species in the reaction. And so do I have the activity series on here somewhere? I just want to get like a snap, like a little bit of it here. I don't want the whole thing, but I might have to. We'll just use this one. It's not the IB one, but you get the idea. Okay. Metals want to lose electrons. Okay. So that means the most reactive metal wants to be positively charged. Okay. So what this means that is if lithium reacts with NaCl, Na is currently positively charged, and lithium, because it's more reactive than sodium, will force sodium to take its electron. So you end up being Na plus LiCl. Okay. So the more reactive metal gets the positive charge in the end. If it already has the positive charge, then no reaction occurs. So that's what you want to think about. Simplify it. In an activity series, if it's more reactive metal, that means that in the products, it should have the positive charge because it's able to force other atoms to lose their to take on their electrons. So lithium will be able to will force any of these elements below it to accept electrons so it can become positive. But sodium can force all the ones below it, but it can't force calcium, potassium, or lithium to take on its electrons. Yes, Cass? No, you don't need to memorize this. You will be given this to you in your data booklet. Your data booklet has a whole page dedicated to reactivity series. Yes? No. Just that it is most reactive. Yes. So with that, you're really just looking at, like, if I broke this down, I would write this as Li plus Na plus yields Na plus Li plus. That's really what's happening. The CL is not really changing. And yes, like Andrea asked, they might give this to you in a multiple choice where they say like X reacts with Y plus and forms X plus plus Y. If you see this reaction, what that tells you is X is more reactive than Y. That's what that reaction tells you. If you see Y reacts with Z plus and you get no reaction, then that means Z is more reactive than Y. So what else would you need to know in this information here to be able to come up with an activity series? What other reaction would you need to know to figure out what is the most reactive and least reactive of these metals? Between X and Z. So you need a third reaction that says, okay, is X more reactive or Z more reactive? So if I had something like this, Z plus X plus becomes Z plus plus X, then Z is more reactive than X, which is more reactive than Y. Does that answer your question, Andrea? Okay. Because is that what was kind of bothering you about that?
Yeah.
Kind of the application of the concept.
So they can do this with equilibrium too, right?
What do you mean?
I didn't think of it wrong, because like when we were doing the data booklet thing, we were writing like equilibrium stuff and then we did this, but maybe it was the activity series.
Yeah, I think, yes, I believe so. No, that's okay. Yes, Daphne.
Can you please explain which one is the best oxidizer?
Okay, so good question. All of these we're assuming are metals, correct? And metals want to oxidize, because oxidation means losing electrons. So whichever metal ends up being positive the most often ends up being the best oxidizer. Z. So Z here, notice Z stays positive here, Z stays positive here. That's the best oxidizer. So you say Z is the best oxidizer. Okay? Now, conversely, Z plus is the worst reducing agent. Because it's so good at oxidizing, it's not. Wait, actually, hold on, let me say that again. Sorry. I got to hear myself here. Hold on. Yes. Z plus is the worst reducing agent because it doesn't want other things to oxidize with it. Okay? So the best oxidizer is also the worst reducing. The ion of the best oxidizer is also the worst reducing agent. Because it doesn't want to it doesn't want to accept electrons. So yeah, in this question, you would say Z is best oxidizer, but you would say, oh, maybe I'm not saying reducing agent. I should be saying oxidizing agent is worst oxidizing agent. Yeah, I had that backwards. Okay. That means it's the worst reducer, which also means best oxidizer. Let me say that again, okay? In this scenario, Z is the best at losing electrons, right? So therefore, that means the ion of Z is the worst at gaining electrons because it doesn't want to gain electrons. It wants to stay positive, okay? So you would say Z is the best oxidizer, but Z plus is the worst oxidizing agent because it's the worst reducer. Okay, yeah, let me say it again. Okay, let me try to explain it. Okay. Do we agree that Z is best at losing its electrons? Okay. What that means is Z plus, if this is the best at losing its electrons, then this is the worst at gaining electrons. Because it doesn't want to go back to Z, it wants to say Z plus, right? So if it's the worst at gaining electrons, then it's the worst reducer, which we also call the worst oxidizing agent. Because those mean the same thing. Sorry, I got y'all down the wrong path originally. Mistake number one in my lifetime.
Would it be wrong to say that the one that's more reactive is the one we want to be ion?
No, that's fine with metals. Actually, even no, that works for everything. Yes, because at first I thought you said positive ion, but no, if you just say ion, that is correct. Whether it's a non-metal or metal, the one that ends up the ion is the more reactive of those. Yes, that is a safe way to simplify it. Actually, second mistake. The first mistake was agreeing to teach chemistry. I don't know if I picked that up. I hope not. Okay. All right. Questions about that? Okay. One quick thing for HL. Okay. And I'm probably going to stop here. I'm not going to go into organic chemistry. I think y'all have seen enough organic chemistry for a while now. Okay. So topic 19, HL. So SL, you're done. I guess everyone here is HL, so it doesn't really matter. Okay. So no one's going anywhere. Topic 19, HL has you calculating cell potentials, okay, of voltaic cells. Okay. And so the one thing I want to emphasize here is understanding that what a reaction that's a reduction reaction is and what a reaction that is an oxidation reaction is. And so when you look at the data table, this is just a snippet of it, but you get the idea. I think it's like 23 or something like that, 22 or 23. We'll look at it. Hold on a second. Let's see, get to know you dad. It's 24, thank you, 24. Okay. These are all reduction potentials. I don't like the titles here. I think it's confusing. Okay, so ignore this. Okay. But all of these reactions are reduction potentials. So if you're looking at Li plus electron yields Li, that has a reduction potential of negative 3.04, which is a very bad reduction potential. But what that also means is that Li yields Li plus electron is positive 3.04. So this is a really good oxidizer. Okay. Now, the only thing you can do to cell potentials is change the sign. That's it. It doesn't matter what the coefficients are. It doesn't matter how many electrons are transferring. The only thing you can do is change the sign. It's not Hess's law where you double the cell potential if you double the number of Li plus ions. So all you can do is flip the reaction around. What I want you to think about is this, okay? If I look at Li here and I look at K, oops. If I compare these two right here, okay, notice that they are both oxidation reactions, okay? So those are oxidation potentials. Now, what is the better oxidizer? The top one, Li, lithium, because it has a higher oxidation potential, it's more positive. So it's the better oxidizer, which means if you were to put these reactions together, you would need to flip, the K to force it to gain an electron so that it's negative 2.93 here. And then the cell potential is 0.11 overall. The same. Yeah, I would, to avoid confusion, I would always make them the same type of reaction, and the more positive one is the better one, and the less positive one is the worst one. Yeah. So when I'm comparing two reactions together, Alexandra, I want the electrons to be on the same side so that I know these values are comparable. And if they're on the same side, the number that's more positive means that whatever reaction you wrote here, it's better at doing. And so here, I wrote both these oxidations, so the more positive one, 3.04, means this is the better oxidizer, so I can flip this reaction. There you go. Also, and I'm going to put the whole screenshot down here because I think you need all this. Don't forget, in this chart, there is the reduction of water and the oxidation of water here as well, because you need those two for the electrolytic cells and aqueous solutions. So remember, the water's on the right here because this is supposed to be oxidation, so you actually have to flip this reaction around and change the sign to use this. But this is water's reduction. So these are the two equations you'll use in electrolytic cells. So you don't need to memorize them for the most part because they're given to you in the data book for paper 2. I guess theoretically they could give it to you in paper 1, but for paper 2, it's definitely present there. Questions about that? Yes, Alexander. Yeah, the cell potential formula is what we say. Oh, I didn't realize it was so small. Oops. Okay. I don't know if it's gonna scale. Okay, it does scale. I say it is this. The E cell is equal to the E oxidation potential plus the E reduction potential. I know that some books teach it differently. Some books will keep everything in reduction potential and then just subtract the oxidation. I think that's a little confusing. I would rather flip the reaction, change the sign, and then just add the two values together. So this is the way I teach it. But some books will say E reduction minus E of oxidation, or sorry, like E reduction here, which is really the oxidation value. So they write it differently, so it looks like that. But it's the same thing in actuality. It gets you the same number if you do it, but just don't do both. Don't flip it and then subtract. Yes. Okay. Oh my goodness. Okay. That's it for minimize what you have to memorize for this. I know that was 3 hours. Sorry about that, but a lot of these different ideas that you need to kind of keep in mind. Okay, stopping the recording now.